Hi everyone, so this is a review for Chapter 7 revision quiz. So based on the responses we have here, I think we'll be discussing question 5, question 11, question 12, question 13, question 18, and question 20. 6 questions this time, so it will be a bit long, so bear with me. Question 5. Question 5 says two stars X and Y masses 9m and m are separated by a distance d. Okay, so since the picture is small, I'll draw it here. 9m and m separated by a distance of d. So what is the distance x of point P from X, where let's label this X and Y to avoid confusion. So what is the distance X of the point P from X? Okay, small x and big X. Be confusing. This is X, where the gravitational field strength is 0. So we want to know if the acceleration due to gravity is equals to 0 at this point P. Okay, so we know that we will need to express x in like number d. Okay, so instead of just saying that x like this, let's call it xd then, and things will be much easier. Let's call it xd, so later x will become a number. Okay, so this one can call it yd. Okay, then we know that later x plus 1 will be equals, x plus y will be equals to 1, because they all add up to become 1d. Okay, knowing that, let's try to digest everything right now. Okay, so we know that a g will be equals to 0, but this acceleration due to gravity here consists of two components. One is the gravitational attraction because of the planet X, and one is the gravitational attraction because of planet Y. Okay, so we usually assume the right as positive, we assume the left as negative. So in this case, we know that AY minus AX will be equal to 0. In other words, they should cancel each other out. Okay, once we know that, we move things around and start substituting things inside. Okay, AY, which is gravitational field strength due to Y, you can call it as G. This thing is having a mass of m, this thing is having a mass of 9m. So G times m divided by y d squared. Whereas for ax, which is the acceleration due to gravity for planet X, will be g. The planet X will have 9m divided by the distance is x d squared. Okay, so it's time for us to do a bit of manipulation. So gm over y square d square is equals to 9gm over x square d square. Why did I write capital M? This is small m. Okay, so we can potong a gm, potong a gm, and potong a d square, potong a d square, and now something comes up. 1 over y square equals to 9 over x square. We subsume everything, it will become x square equals to 9y square, which if we square root both sides, will become x equals to 3y. Okay, we also say that x plus y is equals to 1. So x plus, since we know that x is equal to 3y, we can say 3y plus y equals to 1, and therefore for y equals to 1, therefore y equals to 1 over 4. Okay, but what we are asking here is the distance x. We are looking for this thing here. So x is just right here. We are spending a lot of spaces there. Okay. Since we know y is 1 over 4, then x is just 3 over 4. Okay, so then we can insert this number 3 over 4 here. So we know the answer will be D. Okay, again, it's just manipulating the symbols and stuff. This thing is very difficult to teach. I think it will come by practice somehow. So there's a lot of questions like this. So by more practice, you'll be able to do this kind of question. Okay, question 11. Question 11, an orbit of a satellite is close to the Earth's surface. Okay, so the satellite is close to the Earth's surface. If the radius of the Earth is r, and the gravitational field strength on the Earth's surface is g, then the speed of the satellite is given by, okay, this thing I think is similar to a tutorial question, so I'll very briefly go through it. You know that the velocity of a satellite will be equals to gm over r. Okay, and you also know from this sentence here, gravitational field strength on the Earth's surface is g. Okay, gravitational field strength on the surface is basically g, then the mass of Earth divided by the radius of the Earth squared. Okay, this is ag equals to gm over r squared. And now they tell you that this ag on the surface is equals to g. So now you know g is equals to gm over r squared. So now this is the equations that we know for the velocity of the satellite. And what they are asking for here is expressed in terms of small g. It means by we want to remove small g and want to remove big G and bring in small g. So in that case, what we want to do is we want to find the expression of big G in terms of small g. So later when we substitute this inside, we can remove the big G and let the small g come in. Okay. Now let's do it. The big G, we replace it with g r squared over m. Then we have m over r. Okay. Now it's a matter of cancellation. Square square. Now you're left with g r. And that is the equation that we're asking for. So the answer will be this. Okay. So now let's move on to the next question, which is question 13. Question 12. Okay, sorry. Question 12. Question 12 says, the velocity required to launch a satellite into a circular orbit around the Earth at a distance r from the Earth is bs. Okay, so it means by this is the velocity that we usually get, b over gm over r. Or if you are not familiar with this, this is our satellite. This is our satellite. Then this satellite is moving with this velocity s. Okay, if a space vehicle is launched with a velocity v as shown in the figure, and v is less than bs, okay, there's no figure, but what they tell you is this v is less than bs, means by bs is the speed needed for you to go around in uniform circular motion. So if you launch something with the speed less than the speed needed for circular motion, what will happen is So this is a bit of theory, probably never heard of it, but yeah, you can think of it like this. This is your Earth, right? If you are launching something, let's say you are at here, you want to launch this satellite. If you push it to the side with an initial velocity of v, okay? If this initial velocity is small enough, is too small, what will happen is it will drop to Earth, right? Make sense? Okay, it will drop to Earth. Then if you push it slightly harder, then it will drop further away from the Earth. Now if you push it at the right speed, what will happen is it will constantly falling towards Earth, but because the radius of the uniform circular motion is big enough, it constantly falls towards Earth but not touching Earth. It's constantly falling. It's like falling this way, constantly falling this way. But since the radius is big enough, it doesn't really touch Earth. Instead, it completes a circular motion. So this is the suitable V that we can find using V equals to Gm over R. Okay, so if you go over this V, if you go over this square root Gm over R, what will happen is you might be going on a circular, on an oval path. Okay, that's why this is not your center anymore. Just now, this is the center for this one, right? For this circular path, this is your center. But once if you push harder, what will happen is the orbit will be elliptical, and if you push even harder, it will not be attracted. In that case, it's escaped from the Earth. Okay, so it's a bit out of the syllabus actually, but what you need to know is, if you happen to know this is the orbital velocity. If you know the orbital velocity, and you know something is being launched with a speed, with a velocity less than this, what will happen is it will fall towards Earth. If something is launched with a speed greater than this v, what will happen is it will probably be an elliptical orbit. Or if you're even greater, it might just escape. Okay, so just to keep it quite clear, if this is your Earth, then the orbit will be something like this. Ouch. This one, it's basically escape, not coming back anymore. If this one is probably falling towards Earth. Okay, this one will maintain a circular motion. Okay, so this is the idea behind the velocity of the orbit, the orbital velocity of the satellite. This is the idea behind it. So they say that in this thing, they say that the velocity is less than vs. In that case, under this case, it will fall towards Earth. So the only case appropriate for this situation is C. Okay, next question. Question 13. Okay, question 13 is a bit long. Okay, let's digest it one by one. So you have 3 satellites, which is X, Y, and Z. Okay, they are in circular orbits of radius R, R, and 2R respectively. Okay, so the masses of the satellites are M, M or 2M, and M respectively. The period of the orbit of the satellite X is T. So Tx is equals to T, Ty, Tz. They didn't tell you anything about Ty and Tz. They tell you that the period of the orbit of the satellite Y and Z are Ty and Tz. Which of the following is correct? Okay, so as you can see, we need to find something regarding Ty and something regarding Tz in terms of Tx. the orbital x. So let's start. Okay, so you know the equation for period will be t equals to 2 pi square root r cubed over gm. Okay, so this okay, so this is the equation, the general equation, general formula. Let me keep it quite clear. This mass here is the mass of satellite. Okay, now let's find Ty in terms of Tx. Okay, Ty again is 2 pi, but it's r of y cubed divided by g m y. Okay, so an interesting thing here, which I think a lot of you might make a careless mistake, is thinking that this is the mass of the satellite, but this is not the case. This is the mass of planet. In this case, our planet will be Earth. So does the Earth mass change? No. In that case, this capital My will be actually just equals to mass of Earth. So in this case, Ry is still R, Ry is still R. So we can continue and say that it will be equal to R over Gm. And this is exactly the same as T. Okay, this is exactly the same case as T. Okay, because Tx, okay, I didn't do Tx, I probably should do Tx. Tx is basically just 2 pi Rx cubed over G mx. And since the mass of Earth doesn't change, it will just be 2 pi. And since the radius is R, it will just be R cubed over Gm. And we call this thing T. And this thing is equals to this thing, that's why Ty is also equals to T. Let's look at Tz. Tz is 2 pi Rz cubed over Gmz. Well, all these things doesn't change except for Rz. So we keep it like this. So Rz, from the equation we know that Rz is 2r right now. Okay, it's twice the radius of satellite x and y. So we put 2r cubed. Then we further doing this, 2 cubed will be 8. So it will be 8 r cubed over gm. And if you do a bit of manipulation, maybe 2 pi, I take out this 8, the square root of 8, I take it out. So this one I keep it like this. So you can see that this term here is just our t. So what I can do now is just call this square root of 8 t. And square root of 8 happens to be 2.8 t. So we can find from here that ty is equals to t, whereas tz is equals to 2.8 t. Okay, so if you try to match this answer, we will see that this is the answer for C, am I right? Yeah, this one. Okay, so again, a bit of manipulation, a bit of ratio, then you should be able to get the answer. Okay, question 18. Question 18 asks about escape velocity on the planet is v, if the radius contracts to 1/4 of the present value. Okay, the old situation, escape velocity is v, then you have your radius, which is r. The new situation, you have your new escape speed, and your r is now the 1/4 of the whole r. Okay, your mass doesn't change, so your new mass is just equal to the old mass. So now they ask for the escape velocity. You know the escape velocity is just v over 2g m. M is the mass of the planet over r. So let's try to do, I shouldn't use small m, I should use big M since it's representing planet. Let's try not to be confused. Mass of planet is equal to mass of planet. The new mass of planet is equal to the old mass of planet. So now let's try to build a new situation. That'll be 2g m prime over r prime. 2g doesn't change, it's constant. M prime is now equal to m, so m, whereas r prime is equal to 1/4 of r. Okay, if you do a bit of manipulation again, it will be 4 times 2g m over r. This will be square root 4 times 2g m over r. This 2gm over r is basically just v. So square root of 4 is 2v. Okay, so the answer will be, the new velocity will be doubled the old escape velocity. So the answer is doubled. Okay, that's question 18 for you. Question 20. Question 20, consider a body of mass m which needs to be moved from an orbit of radius 2r to 3r. What is the energy required? So this, you can think of it like there's a planet probably, and you have a body which is mass m. Right now it's orbiting in a radius which is 2r. Later you want to shift it up to another radius, and that radius measure it will be 3r. Okay, so we move from here to here. That's the idea behind it. So this is like your move a wooden box on the table, move it up 1 meter. Okay, for the box to move up from the table, you need to supply energy. You will need to lift up using external force to lift up the box away from a table. This is the same case here. When you move up from radius 2r, from distance 2r to distance 3r, you actually need to supply energy to allow that thing to go to a higher altitude. Okay, in our normal daily life example, lifting up a box, our hand provides external force. We supply energy to lift the box away from the table. In this case, we need to apply energy to allow the mass to go from radius 2r to radius 3r. Okay, so how much energy do you need to supply is basically the minimum amount of energy you need to supply is just the difference in the potential energy between these two orbits. Okay, so from here to here, you actually gain some gravitational potential energy. You gain some gravitational potential energy, but this gravitational potential energy has to come from somewhere. Okay, so it basically comes from your work done by your external force to move that thing from 2r to 3r. That external force is the one that supplies energy, which will be stored as gravitational potential energy when you move to a higher altitude. Okay, so basically what you need to do is you need to find the change. Okay, you need to find the change in the gravitational potential energy between these two orbits. So you know this is just UF minus UI. By finding this change, you know this is the energy you need to supply in order to make that change. Okay, so this is negative GMM over R final minus GMM over R initial. Okay, now you might see there's a lot of like terms. G and M are all the same. We take out G and M. Then we are left with negative 1 over RF, negative, negative, positive, 1 over Ri. Let's shuffle a bit the equation to make it look nicer. Now, we know that R initial is 2R, R final is just 3R. Move it up. So, it's a matter of substitution right now. 1 over 2R minus 1 over 3R. So, now it's just your secondary school mathematics. I want to make it a common denominator, so we cross multiply. So it becomes 3R minus 2R divided by 6R squared. 3R minus 2R is basically just G and M R over 6R squared. Now you can bottom the R. So you are left with G M M over 6R. And this is your answer for this question. G M M over 6R. Okay, so you might be unfamiliar with this concept that the energy required is the change in gravitational potential energy. But if you have a problem understanding this, think of the simple example where we leave a box above the ground. To lift a box above to another altitude, you need to supply energy. And the amount of energy you need is the change in the gravitational potential energy of the block itself. Okay, it's analogous to what we learned in chapter 5 for the MGH thing. It's analogous. Okay, so that wraps up our 6th question for chapter 6 review. Okay, that's all. Thank you very much. Chapter 7 review. Yeah, so this is chapter 7 quiz review. That's all. Thank you very much.